This is part 2 of the 3.03 review. All right, so we're going to start over with the solve paragraph. And we were talking about acids and conjugate bases. Because all three species can accept a proton, they are all considered Bronsted-Lowry bases. So if we go back up, just to review, we see that the acetic ion is negative, the carbonate ion is negative, and the bicarbonate ion is also negative. So remember, they want to be neutral because acids and bases put together have a neutralization reaction to create something neutral, which would be the salt and also water. The acetate ion's conjugate acid is an acetic acid. Okay, so basically what they're saying is, what would this become if you added one hydrogen to it? Okay, well, you'd get rid of the negative sign because you're adding a positive proton, and you just throw an H at the end. That's it. The carbonate's conjugate acid is a bicarbonate ion. So again, we added an H to it. The bicarbonate's conjugate acid is carbonic acid. Because bicarbonate can donate a proton, it is also considered a Bronsted-Lowry acid. Its conjugate base is the carbonic ion. In other words, bicarbonate ion is both an acid and a base under the Bronsted-Lowry definition. Scientists use the term amphoteric, ampho meaning it can be either, to describe compounds of this kind. All right, you need to do problem sets 1 and 2. Give the conjugate base for each of the following acids: H2PO4, H2SE, HNO2, and HASO4 with a -2 charge. Explain why Arrhenius acids can be considered Bronsted-Lowry acids. So go ahead, write down your answers, hit pause, then I'll go over them. Okay, so all of these are acids, and what do acids do? They donate or get rid of a proton, or they donate or get rid of a hydrogen. So if that helps you out, hit pause now and write your answers again. What are these compounds going to be after they lose a hydrogen? So H2PO4 becomes HPO4 with a -2 charge because it lost a positive proton, so now it's more negative. H2SE, again, we lost a hydrogen, which means we also lost a proton, so we have a -1 charge, and it's just HSE. HNO2, we lose that hydrogen, and we get the negative charge, NO2. And HASO4, -2, get rid of the hydrogen, we also get a -1 more charge, so a charge that's one more negative than it was before. Sorry, I said that a little confusing. So instead of being -2, it's -3. All right, and then our other question said, explain why all Arrhenius acids can be considered Bronsted-Lowry acids. So it's asking you about the definitions. And it says an Arrhenius acid is a species that dissociates, breaks down to produce hydrogen ions or protons in aqueous solutions. A Bronsted-Lowry acid is a species that can donate a proton to another species. So specifically, Arrhenius said you're getting rid of hydrogen ions, but hydrogen ions are the same thing as protons. So really, they're saying it's the same thing. Okay? And then it says, if Arrhenius bases dissociate to produce protons, well, remember, what do they get rid of? They get rid of OHs. Okay? So then they'd have to be able to donate. So I think this last sentence is just more confusing. So I think if you just focus on the first two sentences, that's really the key to the answer. In that Arrhenius acids are producing the hydrogen ions, which is the same as a proton. Bronsted-Lowry specifically is saying they're going to donate a proton. And that's it for the 3.03 review.